So welcome everyone to today's HEP-TN Seminar. It's a great pleasure to have Román Orús from Donostia International Physics Center in San Sebastian and also Multiverse Computing. So today Román's going to give us some news about tensor networks from San Sebastian. So thanks Román for giving this talk, and please, it's all yours.
Thanks a lot, Suki. Thanks a lot also for the invitation to give this webinar. It's a pleasure to see all your names in my screen. Let's put it like that. Okay. Yeah, I'm really very happy to be here. So yeah, I want to explain you about some results that we've been obtaining recently in my group at the DIPC. Together with Said Jaromi, who is our postdoc at the DIPC. I hope you can see my pointer. And also with Philippe Small, who was my PhD student at the University of Mainz. And I'm saying was because he just defended his PhD very recently, and he's going to be moving to Berlin pretty soon as a postdoc. All right. Good. So let me move on. Just for you to know, maybe not everybody here knows where is San Sebastian. This is in northern Spain in the Basque Country. This is a typical holiday destination, all right? We are just 20 kilometers from France, so we are the closest thing to being French without actually being French, okay? It's not a bad place for going sailing. You know, if you like the sea, we are just next to the ocean. The food is also interesting. And surprisingly, here you can also do surfing, but there are also some centers on theoretical physics, such as the DIPC and the surrounding environment, which is very good scientifically. There are also some startups, such as Multiverse Computing. I invite you to see if you can find the Mars Invader in our website. Okay, there's going to be a gift for the guys that managed to find it. Okay, and well, that's what we are doing here at San Sebastian. So this is the outline of my talk for today. It's very ambitious, but essentially I would like to give you an overview of different projects. So instead of focusing on one specific application, we've been working on several things related to tensor networks for strongly correlated systems. And I just wanted to make you a little bit of a summary of different things. All right. So first I will start with some introduction. I don't think I have to introduce too much tensor networks to this audience, but still I'll revisit some concepts, both at the introduction, also throughout the talk. Okay. Then I will explain you about results for two-dimensional simulations for the breathing Kagome quantum antiferromagnet. All right, this is in 2 dimensions using infinite PEPs. Then I will explain you some results for 3-dimensional systems at finite temperature. We developed a very efficient algorithm for doing that. And in particular, we applied it to simulating bosons and also Kitaev models on funny lattices, such as the cubic, the pyrochlore, and also hyper honeycomb lattice in 3 dimensions. I will show you some results concerning this. And finally, I will explain you about benefits and potential problems of simulating 2-dimensional systems with PEPs using SU2 symmetry. All right, this last part was done in collaboration with, actually it was a big part of the work that Philippe has been doing in the last years. All right, I don't know what is usually the format here. You can wait until the end to ask me a question, but I'm happy if you interrupt me in the middle of the talk and ask me, or I don't know, Suki, you can do as you wish, you are the chairman, okay? Excellent, let's move on. So let's start with some basics. As you know, the many-body Hilbert space of a quantum many-body system is way too large. We know this since many years ago. This is a graphical representation of what could be the quantum many-body system. The Hilbert space of such a quantum many-body system. We know that we need to focus on the relevant corner of the Hilbert space. All right, the set of product states corresponding to mean field theory is exponentially small relatively to the size of the overall Hilbert space. The set of area law states is also exponentially small. This is easy. Well, this can be computed by doing counting of parameters, and the set of tensor network states, which is in the middle, is also, of course, exponentially small. All right. So this corner is the relevant corner of the Hilbert space in order to describe quantum matter as low energies, as you know. And it's a set of measure 0. So this is where, you know, ground states and matter at low energies is living. We are living in a 0 measure set of a huge Hilbert space. The situation is even worse than that, as you also probably know, because even if you do time evolution, you cannot reach much of the Hilbert space. This is why some people say that the Hilbert space is a convenient illusion. If you do time evolution from one of these sets in the corner with a local Hamiltonian, turns out that you are only exploring the surroundings of the set, and you essentially lose most of the Hilbert space. The exploration time is exponentially large in the size of the system, and if the size of the system is of the order of the Avogadro number, which is of the order of 10 to the 23, then, you know, the exploration time is order 10 to the 10 to the 23 seconds, and that's exponentially larger than the age of the universe. You know, means that there is a problem here if we want to describe quantum many-body systems using the full Hilbert space, and we need a language to do that. Okay. Well, not surprisingly, the language is tensor networks. You know what tensor networks are. This is just, you know, I'm just revisiting here all concepts. The idea is to pick up the coefficient of the quantum many-body wave function and break it into fundamental pieces. So, you know, matrix product states. This is I always call this the tensor network superstar. This is the type of tensor network that is at the basis of density matrix normalization group, or other algorithms for one dimension, such as time evolving block decimation, TEBD. It's just an array in 1D of tensors. This idea can be generalized to a higher dimensional system, such as two-dimensional PEPs. As in here, sorry, I didn't mention that, well, there are different types of dimensions in these tensor networks. There are physical dimensions that correspond to local Hilbert spaces, and also bond dimensions, which correspond to, you know, the degrees of freedom that are carrying the entanglement, okay? The idea of matrix product states can be generalized to higher dimensional systems. This is a PEP, a projected entangled pair state. And they are at the basis of all the algorithms for 2D systems and also 3D and so on that are using tensor networks. And, you know, here the limit is your imagination. This is an ansatz for critical systems in 1D. This is the multi-scale entanglement renormalization ansatz. Here there is an extra dimension that is holographic. And as you probably know, there are some very interesting connections between the meta, which is this type of tensor network, and also the ADS-CFT correspondence in quantum gravity, right? Since this is a HEP-TN talk, probably this is what is interesting, what was typically interesting in this type of talks, okay? But it's a pity that I'm not going to be talking about the ADS-CFT, okay? I'm just going to be talking about numerical simulations, in particular using projected entangled pair states. And well, you know, description of quantum many-body states with tensor networks are efficient. We have a polynomial number of parameters. Tensor networks obey the area law scaling for the entanglement entropy. And well, it's also proven that this family of states actually corresponds to this corner of the Hilbert space that is relevant to describe matter at low energies. Now, in recent years, well, it's also already not so recent, but every time I give this talk, I have to update this slide. There has been a big bang in tensor networks. They appear everywhere. I tend to say nowadays that anywhere where there is a structure of correlations or variables that are correlated in some way, there must be a tensor network behind, all right? Now, here you have many examples, ADS-CFT and quantum gravity, as I was saying. There are also strongly correlated systems, classical statistical mechanics, of course, for partition functions of you know, classical models. Numerical tensor calculus in mathematics, artificial intelligence. Also, there is a trend of, you know, developing new machine learning algorithms using tensor networks. They're actually more efficient. The training is faster, and they work better for anomaly detection than deep learning. Okay. And also there is another trend, which is to explain neural networks in the language of tensor networks, and I think that is also very interesting. They have also been recently jumped to industry. We've been doing actually some simulations for finance, for computing optimal trading trajectories, and this works, okay? And of course, you know, material science, quantum chemistry, nuclear physics, of course, for quantum simulations, quantum information computation, even I would say industrial simulators of quantum computers are nowadays being programmed using tensor networks, okay? Well, HEP-TN and lattice gauge theories, that's also one of the long-term goals, to simulate lattice gauge theories with tensor networks and so on. Excellent. Let's move on. And those were the basics. Okay. Now let me start explaining the first of the projects that I want to summarize in my talk. The first one has to do with the breathing Kagome quantum antiferromagnet. What is this problem about? Well, in strongly correlated systems, one of the hardest numerical or most paradigmatic numeric models to simulate is the Kagome Heisenberg antiferromagnet. So these are spins 1/2 on the sides of a Kagome lattice. And computing the ground, this system is highly frustrated, and computing the ground state of this model is extremely difficult because the ground state has there are many quantum fluctuations going on, and there was a long debate on what was the correct ground state. It was also a very good benchmark for numerical simulations in 2 dimensions, okay, both with 2-dimensional DMRG or 2-dimensional IPEPs and so on. Now, the breathing Kagome Heisenberg antiferromagnet is the same model, but this time we are giving different coupling strengths to the up triangles and the down triangles. So as you can see here, this is a Kagome lattice, okay? There are triangles that are pointing up, and there are also triangles that are pointing down. And the Kagome lattice is nothing but a lattice of corner sharing triangles. Now, the idea is that we have 2 different types of couplings, and this is why it's called breathing, because depending on the relative strength between one type of triangles and the other, we may have interesting phases going on. All right. Let me shut down my WhatsApp because it's popping out all the time. And okay, that's much better. Okay, so this is the model that we are going to be considering for a spin 1/2. Now, why is this model interesting apart from purely academic reasons? Well, first of all, because in nature there are lots of candidates for Kagome compounds, but it's very strange that they have exactly the same coupling for the upper and the lower triangles. So Kagome compounds tend to be anisotropic in nature, all right? There is also a candidate material for this breathing Kagome model, all right, which is this vanadium oxyfluoride compound. Here you have the nice formula. This has been worked out actually in experiments, okay? There are some very nice experimental papers about this. And then there is a fundamental question here, which is whether this model, these Heisenberg antiferromagnets with breathing anisotropy, whether they can host quantum spin liquids, also in the same way as the standard Kagome Heisenberg antiferromagnet has. Now, experimentally, there are signatures that at this ratio of the couplings, around 0.55, there is a quantum spin liquid, okay? And then, of course, the question is, for very large anisotropy, this picture may break down. For very small anisotropy, it may be a different one. And at some point, when this is exactly equals to 1, we have the usual Heisenberg antiferromagnet, and we know it's a spin liquid. So the question is whether there are phase transitions, which type of phase transitions do we have, which type of phases do we have, and so on. Okay. 1 second, much better. All right, let's move on. Okay, well, we studied this model with infinite PEPs and with infinite project entangled simplex states. You can find the results in this very nice paper that was published in SciPost. I just noticed that there is an O missing here, and this is because my keyboard in the Mac is doing funny things nowadays. But this is SciPost, okay? This was a paper with Said and also with Didier, Paul Blanc, and Frederic Mila. We did a very detailed study of the model, okay, as a function of of the parameters and of this anisotropy. So the first thing that we did was to simulate the model at equal couplings, all right, in a small breathing limit. This is just the plain Kagome Heisenberg antiferromagnet. This was just for benchmarking our algorithms. We programmed different options here, such as projected angle simplex states with simple environment. This is some mean field environment. It means we didn't compute the environment exactly using corner transfer matrices or anything like that. We were able to go up to bond dimension 18. Also with projected angle simplex states plus CTMRG for the environment, we went up to bond dimension 13. These are these dots here. and also simple update plus corner transfer matrix normalization group with PEPs instead of project entangled simplex states. Those were these dots in here. Now, this was for benchmarking purposes. You can already see that for PSS plus CTMRG, we were actually getting the best results, and they're approaching the best results so far, which are the ones that are obtained, well, the ones obtained with PSS by the Chinese group, and also the DMRG, the 2D DMRG results using SU2 symmetry from some years ago are the ones down here. Now, we know that this is a gapless quantum spin liquid. The decay is algebraic here, and this is, or people take this as a signature of having a gapless phase. It was already clear from the MRG calculations that this was a quantum spin liquid. Which type of quantum spin liquid? Well, I think you have a reference for each one of your preferences here. I'm just making a summary. Some people claim that it's a U1 QSL with PEPs, with DMRG, also with variational Monte Carlo. But also PEPs people say that it's a Z2 quantum spin liquid, okay, and also with DMRG. So, well, it depends on which paper you prefer. Excellent. Now, we turn on the anisotropy and went to the large breathing limit. We studied different, actually we scanned the whole parameter space. But for instance, this is the type of thing that we find when the breathing is very large. Okay, this anisotropy is of the order of 0.01. So, you know, there are some triangles that are much higher in energy than the others. In particular, the upper triangles are much higher. This is a scaling of the ground state energy as a function of 1/d, where d is the bond dimension of the PEPs. Again, for different types of simulations, here, simple update plus CTMRG, full update plus CTMRG using PEPs, and also project entangled simplex states plus CTMRG. And this is compared with different other numerical simulations also for this point, okay? These are these ground state energies here. You can see that our ground state energy, the best one, is this one that is coming down. And here you can zoom in. Is the one that is obtained with project entangled simplex states, actually, and using CTMRG. And it tends to be the same energy or very close to this one down here, which is the DMRG calculation, all right? So from our simulations, the phase that we were obtaining here was a nematic phase. We had this type of pattern in the ground state. So nematic means, well, that the translation symmetry is preserved, right? But the rotational symmetry is broken. And this is exactly also the type of state that was being obtained in using DMRG, all right? So yeah, our simulations were very accurate, and we were very happy that we were actually getting the best energy. We were getting lower energy because these numbers are variational, okay? So we were getting better energy, better variational energies than all these other approaches, and we were getting very close to the actually 2D DMRG results, which were actually, you know, on a cylinder. So this also should be taken with a little bit of care. Now, from our simulations, as I said, we think that this is a gapless nematic phase. There are other proposals also with PEPs. Some people say that this is a valence bond crystal or a gap Z2 quantum spin liquid, but we find a nematic phase, okay, in accordance with DMRG. Okay. We found also a quantum phase transition that seems to happen around 0.05 for the anisotropy, okay? This is the spin-spin correlation function between Nielsen spins, and we see that this exactly happens for different triangles, and we see that this transition happens around here, and that's around 0.05. Now, this is very interesting because it's compatible with the fact that the experiment had measured a quantum spin liquid at 0.25. So we know that at 1, it should look like a quantum spin liquid. The experiment says that around 0.55, this also looks like a quantum spin liquid. So from our simulations, what we see is that the phase transition is somewhere around 0.05, okay? I have to say that there are other simulations with our methods that claim that the phase transition is somewhere else. But with PEPs, to the best of our accuracy, this is what we were able to find. Something also very interesting is that we computed the correlation functions for the nematic phase, and what we saw is that they look like critical. This is something very hard to obtain with PEPs, but we computed these 2-point correlation functions for the ground state that we obtained, and along the direction of the strong bonds, we obtained a decay that, well, you know, it's gonna go to 0 very fast, of course, because we are talking about a PEPS, but it's significantly slower than what we typically get for an exponential decay. So it's actually compatible with a power law decay. We computed this for up to 100 of sites, and the exponent was around 3.5. So we have something like a gapless thematic phase here on the left-hand side and a gapless quantum spin liquid, and the phase transition is around 0.05. Okay, so that was our conclusion. According to PEPS, we obtain a nematic state compatible with DMRG. It looks like gapless, and the transition is around 0.05. Good. Let me move on to the second topic of my talk. It's actually, well, point number 3, but it's the second topic, which is simulations at finite temperature for bosons and also for Kitaev models. Good. Let's see. Well, we took infinite PEPs and we generalized it to higher dimensional systems, in particular to 3D. Now, some time ago, a couple of years ago, together with Said Jaromi, we developed, I'm not citing it here, I actually forgot, but it's the same authors, okay? One is me, the other is Said, so we should be fine with that, nobody should be upset. We developed a way of automatizing the different updates on a PEPs for very complicated lattices. And in this way, we could achieve, we could run very automatically simulations for very complicated structures in 3 dimensions, such as the pyrochlore lattice, hyper honeycomb, hyper octagon, and so on. Okay. So we had that for ground states. We generalized that for thermal states in order to have, finite temperature behavior and be able to study thermodynamics of higher dimensional systems. So this is what we did. We did 3-dimensional thermal infinite PEPs for funny lattices. Okay. We did it, for instance, for the pyrochlore lattice, which is the one that is right here. Of course, we did it also for the honeycomb. The way in which we computed this was exactly as you will do it in 1-dimensional systems. You do an imaginary time evolution with the Hamiltonian for a tensor network with bracket degrees of freedom for half of the temperature on one side, half of the temperature on the other side. And at the end, this is the way in which you can reproduce a thermal state. All right, starting from a thermal state at infinite temperature, which is nothing but the identity, standard trig in tensor networks. All right. This is the way the update goes. Okay, so there are gates on Ket and Bra indices. This is, for instance, for the cubic lattice, simple cubic lattice. And the only thing is that at the end of the day, in order to compute expectation values, or even to do the updates, you say, well, since you are in 3D, computing the environments is going to be very complicated. And it's true. It's already complicated if you have the simple cubic lattice. One could do 3-dimensional versions of CTMRG. It will be possible. But now, if you want to do this for the pyrochlore lattice, it looks like hell. Okay. So we actually did a simplification, which was to consider mean field environments, all right, in our simulations in order to estimate expectation values and also to do the updates of the tensors. Okay. Now, this is a very, I would say, radical approximation. But I have to say that since we are working with a higher dimensional system that has a lot of connectivity, plus we are working at finite temperature, turns out that this works very well. Okay, it actually works remarkably well. So the approximation is actually not too bad in this regime. And well, and the approximations were also done using the simple update, as you can imagine, as I was saying. Excellent. Good. So what did we do? We took this algorithm and simulated several models in 3 dimensions at finite temperature. The first thing that we did was to simulate bosons. The Bose-Haber model, exactly this model. So we have bosons that are hopping between different lattice sites I and J. We also plug in some density-density interactions, and there is a chemical potential in order to control, the filling fraction and the number of bosons that we have. We consider hardcore bosons, which are equivalent to spin 1/2, and we also consider simulations for softcore bosons. And we did it in different lattices. We did it on the cubic lattice, and we did it also on the pyrochlore lattice, and we computed the thermodynamics of the model. All right. using tensor networks. So this was a very nice calculation. It was very clean, and it was already very useful to show that this approach is actually producing very accurate results. Here is an example of what we get for for soft-core bosons, up to 2 bosons per site for the cubic lattice. This is a typical phase diagram where you can see 2 different mode lobes. Here is the chemical potential. Here is the hopping. This is at 0 temperature. All right. This is a typical phase diagram of the Bose-Hubbard model. You have 2 lobes, okay, because we have occupation number up to 2. You can have, well, exactly, you can have occupation number up to 2. It means that the local dimension is 3. All right. This star here is the tip of the first mode lobe. Okay. This is a typical place where many interesting thing happens. And well, what we did here was to switch on the temperature. All right. And this was for the cubic lattice. So once you switch on the temperature, you can see that this coherent picture of the mode lobes disappears. So this is for temperature over U is 0.05, 0.1, 0.2, and so on. And eventually you just get here a thermal phase transition to a normal gas phase. All right. Now, this is also a plot of the superfluid density, and as a function of the temperature, and also as a function of the chemical potential, and also rho 0, which is the density of particles at every site. So you can see that the superfluid density at T equals 0, it just follow, you know, this is one lobe, this is another lobe, okay? Now you switch on the temperature and the first lobe disappears, and this lobe disappears, whereas the second one actually becomes smaller. So the superfluid phase is shrinking when you switch on the temperature, as expected, and you start having phases here in the middle that correspond to a normal gas phase. So, you know, you have the mode insulator to superfluid transition. When you switch on the temperature, you have some phase in the middle where you are neither in a mode insulator nor in a superfluid, all right? And this is the normal gas phase. That was for soft-core bosons on the cubic lattice. Oops, sorry. We did also simulations on the pyrochlore lattice, because, well, you know, it was within reach. In this case, we did for hardcore bosons. So this is the mode lobe for different temperatures. At 0 temperature, it's very big. And we have the superfluid to mode insulator transition, very clear and very sharp here. As we switch on the temperature, we can see that the superfluid is shrinking as expected, and the normal gas phase starts to appear again until eventually, you know, the superfluid just disappears. This is rho S again, the superfluid density, and this is the occupation number, right? Excellent. What we did next was to consider a different model, since we have an algorithm for computing thermodynamics of 3D systems. A very interesting system is the 3D Kitaev model, okay? Now, the Kitaev model is typically defined on a honeycomb lattice in 2 dimensions. So these are spin-1/2 spin-spin interactions that are isotropic. Depending on the bond, they can be XX, Y, Y, or ZZ. Now, it turns out that the Kitaev model can be generalized to other lattices, trivalent lattices, both in 2D and also in 3 dimensions. There are many very nice papers by Simon Treps and Maria Hermans about this. In particular, what we consider here was the hyper-honeycomb lattice, which is this one here. It looks very much like 2 stacked honeycomb lattices that are coupled in some way, you know, with some links. So there are a couple of reasons why we consider this lattice. First, because it's relevant for experiments. There are some compounds, such as this one, beta Li2 iridium oxygen 3. I really don't remember what is the name of this compound, but we know that this is a proposal to realize the Kitaev model on this hyperhoneycomb lattice is precisely this material. But the hyperhoneycomb lattice is also very interesting because it's proven that the ground state is also vortex free, exactly as for the honeycomb lattice. And then the same machinery that applies for solving the Kitaev model on the honeycomb lattice applies also here. So the model is also exactly solvable in this case. You can take a look at these papers. They explain them very well. This is the phase diagram at 0 temperature. No surprise, the typical A and B phases of the Kitaev model with an isotropic point here in the middle at equal value of all the couplings. Now, when you switch on the temperature, there are different things that happen, but generically, something that people agree that that happens quite in a quite generic way is that the specific heat has a double peak structure. All right. The first peak corresponds to a phase transition. All right. This is the plot that is here schematically. Okay. So the first peak is a thermal phase transition. The second one is a crossover. Okay, between different phases. It's not really a phase transition in the sense that there is no criticality, but there is a crossover here in the sense that there is a second peak. Now, physically, this corresponds to disordering different degrees of freedom in the model. So, you know, in the Gates theory description of the Kitaev model, the first thing that becomes disordered are the Gates fields, okay, and that corresponds to actually the first peak in the heat capacity, sorry, in the specific heat. The second peak corresponds to the actual spins becoming disordered, okay, and then you go from a spin disorder phase to a spin order region, and in this spin order region there is a Gates disorder phase and a Gates order region. Now it's here at low temperature, sorry, where you have topological order. Here in the middle you lose topological order, but still you can have different phases. So what we did was to turn on the temperature and look for this sorry, and look for this double peak structure. Now, here you can find the simulations for high T. All right, at high temperature, we saw perfectly the crossover. Okay, the peak corresponding to the crossover in the specific heat. With our HEP simulations, we went up to bond dimension equals 6. We took as a reference the ground state for the isotropic point. All right, and then turn on the temperature, but we find something very similar also in the rest of the phase, in the rest of the points corresponding to the same phase. Now, for this specific point, we find that this crossover happens somewhere around 0.256. All right, and yeah, the precision was very good. So we see that here there is this crossover. Now, this crossover can also be seen in other expectation values. For instance, the spin correlation functions between nearest neighbors, as in here. But we also computed things like entanglement entropies of very small blocks and so on. And we saw that this is, yeah, exactly there was a crossover here. Now, for the low temperature region, the simulations were harder, okay, because we are very close to be close to the ground state, and it has lots of entanglement here. And I'm not showing them here, but we also find this extra peak. But I have to say that the error was larger. Also because, as I told you before, we are introducing here approximations that are a little bit radical, and they work very well in the high temperature regime. All right. So the fact that we are using simple update plus mean field environment works well because we are at higher dimensional systems and at high temperature. As soon as you lower the temperature and try to reach the ground state, this stops working. Okay. Or at least, you know, it doesn't work so well. So that's the reason why we focus here only on the second peak, which is the one that happens at high temperature. Okay, here is a numerical example showing exactly what I was saying right now. This is the finite entanglement scaling of the position of the crossover temperature and also of the transition temperature. The thermal crossover, you see that as a function of 1 over the bond dimension is, you know, the position is essentially flat. It means that we already reached convergence in this scheme. If you go to the finite entanglement scaling of the thermal phase transition point, you can see that, yeah, we were able to go up to this point down here, and it was still not converged. All right. So you can see that we need much more entanglement in order to reproduce better this quantum phase transition point. All right, or at least not use this mean field environment. So this is something that we are learning for the future. Let me also tell you that we consider in this using this finite temperature algorithm, we also consider other models, such as the Kitaev Heisenberg model on the hyper-octagon lattice. That's also very interesting. I invite you to take a look at the paper to see the results. Good. So let me move on to the last point with content, okay, which is simulations of two-dimensional systems with infinite PEPs implementing SU2 symmetry in the algorithm. Now, here I could extend myself a lot, saying why implementing symmetries can be a very good idea in tensor network algorithms. I will not explain you everything in detail, but the idea, as you know, is that by introducing the symmetry directly at the level of the tensors, then the number of parameters that you have to manipulate in order to you know, to optimize your variational ansatz is actually much less than if you don't introduce a symmetry. Moreover, there is a component of entanglement that depends only on the symmetry, and if you introduce a symmetry directly at the level of the tensors, this is automatically given for free. So if you have a symmetric tensor, which looks like that, what happens is that it breaks into two pieces. Here we have some symmetry operations that are acting on the, you know, the indices of a given tensor. It remains the same. The tensor is symmetric. Now, if we have two legs, means we have a matrix. This decomposes into two pieces. There is one piece that is a degeneracy tensor. There is another piece which is a structural tensor. The structural tensor only depends on the symmetry. Okay. For a matrix, it's essentially the identity. All the degrees of freedom of the tensor, the variational parameters that you optimize, they are all in the degeneracy tensor. Okay. If you have a three-leg tensor, then the composition is very similar, but this time the structural tensor is a three-leg tensor, and a structural three-leg tensor is a Clebsch-Gordan coefficient. All right. So in particular, if we are dealing with, this is general for any type of symmetry, but if we are dealing with SU2, these are the SU2 Clebsch-Gordan, famous Clebsch-Gordan coefficients for changing the basis, okay, between the couple and the between different bases. Now, the degeneracy part is the one that is containing all the parameters of that you have to optimize, and this is the part that you optimize in the algorithm. Now, this is well known for many years already. The point is that implementing abelian symmetries in PEPs, this has been done already for quite a while. Implementing non-abelian symmetries in two-dimensional simulations, it was only the first simulations that started to show up not so long ago, okay? The main reason for this is that it's technically very complicated to deal with, you know, to implement all the machinery, do all the libraries for dealing with all the Clebsch-Gordans and so on, and this non-abelian symmetry in two-dimensional tensor networks, because with PEPs, you know, there is no canonical form or anything like this, nothing simplifies. And then, well, one needs to be very careful with that. Well, we implemented SU2 in general, and implemented it in infinite PEPs. There are different formalisms for dealing with SU2. The one that we chose was the one based on fusion trees, based on a paper actually by Suki. And this, we developed it in more detail in another, it was kind of an anthology, okay? But it was like a manual for developing libraries of tensor network algorithms with SU2 symmetry using fusion trees with Philippe, Suki, and also with Matteo Ricci. And it was published in Annals of Physics 1 year ago. The idea is that, well, we have these fusion split tensors, which are essentially Clebsch-Gordan coefficients, and then any structural tensor can be decomposed in terms of Clebsch-Gordan coefficients only. And this is what we call a fusion tree. Now, once you know the structure of the tree, you don't need to store the coefficients of the tensor at all, because you know that these are only Clebsch-Gordan coefficients. So what one stores in the computer is the structure of the tree and not the tensor itself, okay? Now, this is a very nice computational trick because it allows, well, first, it gives a lot of precision, all right? Since we are not manipulating numbers, only structures. It saves also, you know, a lot of memory, and we don't have to carry the tensor all the time, all right? So this is a very nice approach, and this is what we took in order to program SU2 in 2 dimensions. Now, how do we implement this in PEPs? Well, here you have the typical unit cell for a PEPs, 2-dimensional PEPs. It's a 2 times 2 lattice. This is a small tensor network with 4 tensors decomposes into 2 pieces. Again, the tensor network with degeneracy tensors and the tensor network with the structural tensors. And here the structural tensors are combinations of fusion trees, sadly, you know, in this way. Okay. That's how we did it for IPEPs. For project entangled simplex states, since we were also interested in simulating the Kagome lattice, the composition is very simple because all the tensors are trivalent, and then, you know, we just get the fusion split tensors for free, okay? So these are the structures that we used in order to simulate 2D systems using SU2. Now, what about the results? Let's see. Well, we did a benchmark of the algorithms for different models. The first one was the spin 1 bilinear biquadratic model on the on the square lattice. There is a point actually that has SU2 symmetry. This was studied with a lot of detail by Philippe Corbos and Nissen in this paper from 2017. This simulation was done using U1 symmetry. But the point is that, well, I actually forgot to say at which point it was. Sorry about that. I think it was 0.24 or something like this, the parameter. You can check the paper. Sorry, I just forgot to write it on the slide. But here is the example of simulation that we get. So these are finite entanglement scalings of the ground state energy for different algorithms, no symmetry, SU2 symmetry computing the environment with corner transfer matrices, SU2 symmetry computing mean field environment, so corner transfer matrix at all, extrapolations, and also the U1 numbers from the simulations with Philippe with the same unit cell. All right. Now we saw two things that are kind of interesting here. The first one is that the effect, as we expected, the SU2 simulation, which is the red one, is producing better results than the simulation without symmetry. Okay, that's good. All right, implementing the symmetry brings the variational energy down. Now, second thing that we see is that actually the U1 simulations are giving slightly better energies than the SU2 ones. Okay, now how can this be possible? All right, so we expect the phase to be SU2 invariant, and turns out that the U1 simulations are producing lower energies than the SU2. Well, our interpretation for this is that maybe the SU2 variational ansatz is over-constraining the simulation. All right. So the message here, this is a good example, is that sometimes SU2 symmetry may be too restrictive. And we just found an example in 2 dimensions. All right. We know that the correct ground state has SU2. Well, at least that's what we believe. Still, the U1 symmetry has more variational parameters and is able to produce lower energies. And it's actually very flat also, the same as for SU2. But it was exactly for the same unit cell and we were systematically there. Okay. Now, if you do the same plot as a function of 1 over the number of parameters, you can see this more clearly. Well, we didn't have a number of parameters for the U1 symmetry, but at least comparing with the simulation without the symmetry, we can see that for the same number of parameters, the SU2 simulation actually brings down the energy by a lot. Okay, so it's a good idea to implement the symmetry. Okay, one has to be careful.
Can I ask a question? So why do you get a lower ground state energy with the min fill environment compared with the CTM environment?
No, but that's because that's not variational. Okay, the min field environment is not variational. It's just, you know, you just connect with the lambdas from the simple update, and that's it. Okay, it's faster. I mean, the min field environment, it's only useful here in order to have an idea, okay, of how could be the trends, but it's not physically meaningful because it's not a variational number. It gives you more or less a flavor of how things go, and that's why we plot it here. But it's not a physical number that you give as good. Okay. So yeah, it can be lower. It can be lower, very high.
Numbers should not be trusted.
Yeah, no. For this simulation, no. Okay. At least it can be trusted to give you an intuition of how it should look like, and you can get this number very quickly. Okay. But you cannot give this number as an. There is no way of estimating the error of this number. Let's put it this way. Okay. Okay. So this was for the bilinear biquadratic. Now, we also simulated the Kagome Heisenberg antiferromagnet for spin 1/2, of course, with different algorithms, projected angle simplex states for different unit cells with and without symmetry, with a 3-side unit cell, with 6-side unit cell, with no symmetry and with symmetry, using corner transfer matrices, all right? And here again, we see that when we incorporate this into symmetry, we are able to reach larger bond dimensions and also lower energies. Also here we expect, sorry, a quantum spin liquid ground state. And what we see is that we actually get closer to a quantum spin liquid by using SU2 in the simulations, also in the patterns. So here, these are the patterns of, you know, the strength of the different bonds for these three simulations. The first one is for the 3p SS, the second one is for the 6p SS with no symmetry, the third one is for the 6p SS with SU2. This one is actually getting closer to the quantum spin leap. Now, last but not least, we simulated the spin-2 Kagome-Heisenberg antiferromagnet, which is also believed to have a SU2 invariant ground state. Surprisingly, there are not so many studies of this model. So what we found here is actually something very interesting. Again, we simulated this with projected entangled simplex states with 3 side unit cells with SU2 and without any symmetry. And we see here a very interesting observation, which is that the SU2 symmetry is actually continuing the numbers that we obtained without the symmetry, and the energies still not converge, so we need larger bond dimension. But here it's very clear that with symmetry we can lower down the energy a lot. And actually, what we find is that by incorporating the symmetry, it tends to look like a quantum spin liquid if you have a look at these spin-spin correlations. And when you incorporate the symmetry, the largest the bond dimension, the effective bond dimension that we use, actually the more like a spin liquid it looks like. So we were wondering whether this is actually another instance of a quantum spin liquid ground state for a spin 2. This is a comparison of the energies with and without SU2 for these 3 models. Spin 1 bilinear biquadratic on the cubic lattice, the spin 1/2 Kagome has an antiferromagnet, and the spin 2 Kagome has an antiferromagnet. With no symmetry, this is bond dimension and energy. With the symmetry, this is the symmetric bond dimension, so the bond dimension of your degeneracy tensor. The effective bond dimension, when you incorporate the effect of the symmetry, it can be fractional because this is an average over the different bonds, and they can have different bond dimension, and the energy. And we see that systematically, introducing SU2 lowers down the energy. All right, so it can be a good idea, but we have also seen that for the case of a spin 1, maybe it's over constraining in some cases. Okay, so one has to be careful with SU2 when dealing with 2D simulation. All right, good. That was everything that I want to explain you. These are conclusions. So in this talk, I've told you about 3 or 4 results, namely simulations with infinite pairs for the breathing Kagome problem. We found the phase transition and kinematic phase. Also, simulations for 3D models at finite temperature, for bosonic systems on the cubic and pyrochlore lattices, and also for a Kitaev models on a per honeycomb lattices. Also, the good thing and the bad thing about implementing SU2 symmetry into dimensional PEPS algorithms. And we benchmark, I've shown you that, depending on the system that you want to simulate, you have to be a little bit careful because typically SU2 improves the energies. So it's a good idea to use it, but you have to be careful that you are training your answers, okay? And finally, we've just seen that this spin 2 Kagome has an antiferromagnet may actually be also a candidate for a quantum spin leap. Excellent. So I think I'm on time, and this is everything that I wanted to explain you. So thanks a lot.
Yeah, thanks, Roman, for this very nice and clear talk. Are there any questions?
Yes, if I may ask a basic questions.
Yes.
When you say the SU2 symmetry ansatz is too restricted, do you mean that the ground state actually break SU2 symmetry?
No, what I'm saying is that the ansatz, when you impose the symmetry, this is a constraint that you pose in the ansatz, okay? And the number of parameters goes down. So you have less parameters in an SU2. So if you have a PEPS with bond dimension 10, say, if you don't impose any symmetry, you have a number of parameters, all right? Everything is free, all right. Now, if you impose the symmetry, you are constraining the tensor. There are some sectors that have to be equal to 0, the ones that don't fulfill the symmetry. Therefore, the number of free parameters is less, okay? It goes down, okay? So when you have a symmetric tensor, for the same bond dimension, you have less variational parameters. Now, if you have less variational parameters and you have a variational algorithms, it means that you have fewer directions where to look for, no? And one has to be careful because if you have too few, then you cannot move. and that's what I mean with having over constraining in the parameters. All right, that you put the right structure in the tensor, but maybe you are over constraining it too much and you cannot search variationally for a very good energy. Okay.
Okay, but did say if I take bound dimension 10 with and without constraint, isn't they parameterize the same? If I'm only focusing on, say, I don't know, total spin equals to 0 states, they both parameterize the same set of states. Is it?
No, they are not parameterized in the same way. So think about a matrix, okay? Think about a matrix. It's a tensor with two indices, and now imagine that the matrix is d times d, all right? So if you don't have any symmetry, there are d square parameters, okay? Let's think about that they are real numbers. D square parameters. Now, if the matrix has C2 symmetry, so imagine that you have two sectors, okay? Parity symmetry, positive and negative parity, all right? Then the matrix actually decomposes in two blocks, so positive parity sector, negative parity sector, and then the mixed ones. The mixed ones are going to be equal to 0, and the matrix is block diagonal.
Yeah.
Okay. So the number of parameters that you have is typically half, more or less. Okay. It depends on the size of each sector, but it could be easily half of the number of parameters that you had in the original matrix. Okay. That's what I mean.
Yeah, but if I know the ground state is lying in one sector, then it doesn't matter whether, I mean, I still parameterize all the possible states in this sector with the same bound dimension with less parameter. So the only problem that I see is that maybe there's a problem with the optimization methods, or maybe the ground state break the SU2 symmetry.
I agree. Yeah. So you could start with an initial state that is in the right sector, but then you have to guarantee that you're exactly, so that your optimization preserves the symmetry, first thing, and second, that the ground state is really in that sector. Okay. Yeah.
Okay, thanks.
I see Simone is raising his hand.
Yeah, hi, Román. Thank you for a nice talk. I have just a curiosity. How do you handle with the choice of the sectors? I mean, when you are includes the symmetries, you have to adapt your labels, right, in your open sector.
Yes. Yes.
How is that handled?
We do imaginary time evolution, so they adapt dynamically. Okay, we start with some random sectors, and we just let the algorithm evolve. Okay, so every time it's like in TBD. So we do we apply the gates, and then we we do similar decomposition and truncation, and then the new sectors are becoming populated dynamically as the algorithm moves. Yeah. So it's not a variational algorithm; it's time evolution. Okay, imaginary time evolution.
They are automatically optimized. Thanks.
Exactly. Yeah.
Very nice.
You're welcome.
Okay. Any other questions?
Suki, do you have questions about SU2?
Well, I mean, I could ask a question related to this.
No, thank you.
No. I did actually.
Okay.
But related to this restrictive, like you find that this incorporating the symmetry restricts the simulation. So did you, and in the cases where you observed this, did you find a difference between different update schemes?
No, we didn't. This was a surprise that we find this. I mean, we understand that it brings down the energy. I mean, there could be different explanations for this. We think that the ansatz may be too restrictive in 2 dimensions because the percentage of parameters that is reduced when you incorporate such a big symmetry, it's much higher in 2 dimensions than in one dimension. So the ansatz is more restrictive. The symmetric ansatz is more restrictive in 2D than in 1D. Okay. But on the other hand, it could also be that, well, maybe the best calculations seem to indicate that the ground state is SU2 invariant. All right. Well, what if it isn't? Okay. Maybe we don't know, and it actually breaks SU2. All right, because it's very suspicious that the U1 simulation is systematically epsilon lower. So yeah, we don't know.
Mhm.
I see a hand here, Johan Friedrich.
Yeah, are there any considerations? Sorry, I just started to speak about fermions in 3 dimensions.
Oh, that's a good question. We are doing that. We are doing that. Yeah, there is nothing special about it. I mean, you just you know, we can do fermions also with tensor networks using the language of fermionic tensor networks, fermionizing your algorithm, replace the crossings in the tensor network by fermionic swap gates, implement Z2 symmetry, and then you can do fermions. All right. So we're actually working on a fermionic version. Yeah.
Okay. Cool.
And there is nothing special about fermions.
Yeah, it's a bit more tedious, but yeah, in principle.
Yeah.
Sure.
So I mean, we did the fermionic. We did the bosonic Hubbard model in this pyrochlore lattice and so on. We could also do the fermionic Hubbard model. Well, yeah.
All right. Thanks.
A priori. More questions, comments, provocations?
Just side questions, may I, if I may?
Mm-hmm.
It seems to me, so isn't it the case that when we go to higher and higher dimension, the quantum effect becomes lower, and at the same time, the price we need to pay for the entanglement using tensor network kind of ansatz is also higher? Do you think it's a correct or an effective direction to use tensor network to study 3D quantum systems, or do you think there might be other more efficient way?
I think it's a good way to go. Yeah. So the bond, there is this trade-off between dimensionality and bond dimension. The higher the dimensionality or the connectivity of your lattice, the lower the bond dimension because of entanglement monogamy. We actually see that in the simulations. It means that, you know, all these complications that we have in 2D of computing environments and so on, at some point, if you have very high connectivity, it's just, you know, it's not so important anymore. So I think it's there may be other methods that are also very efficient, okay? But definitely tensor networks for higher dimensional systems are a good approach. Yeah.
Okay, thanks.
You're welcome.
Okay, I think Suki's internet connection got broke down. So then finally, let me thank Roman again for this very nice talk.
Yeah, thank you.